Now, these reactions here can be classified as exchange or metathesis reactions. What's the exchange? Well, it's simply the exchange of counterions. So if I looked at the two cations, they have two anions that are associated with them, but then on the other side, we simply swapped the anions. That's an exchange or a metathesis, where metathesis essentially just means exchange. So we can classify it in that way. And so this example that we wrote here, and also this other example shown here, could be written in more succinctly or conceptually, just as an AX with BY, and then we simply swapped out, the X and Y. If X and Y are the anions, we simply swapped the X and Y between the two to generate AY and BX in this case. Now, not all metathesis reactions result in a precipitate. Most do, and there's some reasons for that. So let's take this example here. Sodium chloride plus potassium iodide goes to sodium iodide and potassium chloride, if we wrote it in that way. If we wrote it in the normal metathesis or exchange form, we just took the iodide and the chloride and swapped them. But you notice I have an equilibrium arrow here. There's arrows pointing towards the products and then also towards reactants. Why is it that way? Well, all four of these compounds are soluble, which means that really it's not the discrete compound itself. These are all solvent-separated ions. They're all fully solvated ions, which means that we really just end up with a completely statistical mixture of all four of these compounds. If we were to evaporate off the water, because those ions, when they came back to combine together with anion and cation, would just do so randomly, since all of the ions, cation and anion, are soluble and all solvated. When they came back together, it would just be random, and we would have a statistical mixture of all four of these compounds. Whereas in the case where we form a solid precipitate, as in the lead nitrate and potassium iodide example, when we form a solid precipitate, there's no longer this equilibrium back. Things are not in a statistical mixture anymore. When lead and iodide meet, they form a solid, they fall out of solution, and then you're only left with the potassium and nitrate ions left in solution. So when you evaporate off the solution, you're left with potassium nitrate. And then, of course, you had your solid lead iodide that fell out first. And so that precipitate formation prevents reversibility. Now, I know we're waxing a little bit long in this video, but let's stick with me for a little while. So what we've written so far has generally been just the molecular equations, where I didn't write out the individual ions as being solvated. I simply wrote the formulas with then the aqueous symbols after them, which indicates that the ions are fully solvated. But it's important to be able to write more than just the molecular equation. So the molecular equation here just includes the full discrete formulas. But as we mentioned, the compounds, if they're dissolved in water, don't exist as the discrete formulas. They exist as the fully solvent-separated ions. And so what's more helpful is to write a complete or total ionic equation, where we break up each of the soluble ionic compounds into their solvated ions. And so we take anything that has an AQ symbol after it, and we break those ions up. Now, anything that's not listed as aqueous, so anything that does not have an AQ symbol after it, we do not break it up. We leave it just the way it is. So you notice that lead iodide, which is not soluble, is not broken up into lead and iodide ions. It stays together. But we break everything else up into its individual ions. And so you can see we've got lead ions here, nitrate ions, potassium ions, iodide ions, and they're all written with the AQ symbol after it, symbolizing that they're solvated. On the right side, lead iodide is not soluble, so it just has the solid symbol. And then you have the solvated potassium and nitrate ions. Now, this gets a little bit cumbersome to write all of the ions out, but we can notice something if we do write the ions all the way out in the complete ionic equation. One thing we notice is that the potassium ions don't do anything. They show up on both sides of the equation. Nothing's changed. The nitrate ions don't do anything. They show up on both sides completely unchanged. And ions that show up in a chemical reaction on both sides of the equation in the exact same form, unchanged, not combined into an ionic compound, but just unchanged, aqueous on the left, aqueous on the right, those ions are referred to as spectator ions because they behave like spectators at a sporting event. They look on, but they don't do anything. And what's useful from all of this is to remove or cancel those spectator ions so that we can see more clearly where the actual reaction is occurring, what's actually happening in the reaction. Spectator ions clearly aren't involved since they show up in the same form on both sides. So what is actually happening at a fundamental level in the aqueous solution? And so if we cancel out those spectator ions, if we simply remove them, so there's the same number on both sides, I just cancel them just like I would in mathematics, then I'm left with what's known as the net ionic equation. This shows the actual ions that are participating in the reaction. And here we have lead ions on the left with iodide ions on the left. They come together to form the lead iodide precipitate, which is no longer broken up into its ions. And so this is the net reaction that's actually occurring. It's very important for us to know how to write the complete ionic equation and the net ionic equations. So make sure to review this information, and we'll go through a few examples. So stepwise process for writing net ionic equations. First, write the balanced molecular equation up at the top. Include all of the phase symbols. If it's soluble, write aqueous after it. If it's not soluble, write solid if it's a precipitate. Or if it forms a gas, write G in parentheses. Or if it's water that's formed, because water, we don't talk about it being dissolved in water, we would just put a liquid symbol after it. So write the balanced molecular equation, and then from that balanced molecular equation, go through and break up into ions anything that has the AQ symbol after it. Don't touch anything else, but break those compounds up that have the aqueous symbol after it and break them up into their constituent ions. So for lead nitrate, for example, right, there's only going to be one lead ion, but there's two nitrate ions. So I would put a 2 in front of the nitrate ion when I write it out. I wouldn't just leave it in parentheses. If I'm truly going to break it up into its ions, then I would write 2 in front of the single nitrate ion. Now, remember that only strong electrolytes are written as dissociated ions. So if we do have a molecular species that has the aqueous symbol after it, we don't break that up. If we have a molecular species that has the aqueous symbol after it, we don't break that up. We only break up strong electrolytes. So strong acids, which again we'll talk about later, and ionic compounds that have the aqueous symbol listed next to them. Then we identify and cancel out our spectator ions from our complete ionic equation. And that will give us our net ionic equation. So what happens if all of my ions are spectator ions? And I think we did this on the last slide to some degree. Remember that case where we had sodium chloride and potassium iodide and we ended with that statistical mixture? Well, that was because all of the ions were soluble. If they were all showed up in the same form on the left as on the right, when we write the complete ionic equation, they all cancel and we're left with no net reaction. And so we just end up with a statistical mixture of products. Let's do a couple examples of this. So write the net ionic equation for the reaction of barium nitrate and potassium sulfate in aqueous solution. So you might need to refresh on your naming for this, but barium nitrate and potassium sulfate in aqueous solution. So first off, the balanced molecular equation. So nitrates are soluble. So barium nitrate, we write that out. It must be soluble, so it has the AQ symbol after it. Sulfates are soluble unless it's one of our exceptions, which potassium is not. And so potassium sulfate is soluble, so we write AQ after that. And then we identify, just like we would for a precipitation reaction, is there going to be an insoluble product? And we find that barium sulfate is. Sulfates are generally soluble, but barium is an exception. So barium sulfate is insoluble. And I'm left then with potassium nitrate. And of course, I have to balance their equation to make sure that that my equation is balanced and the same number of elements are on both sides. That's now my molecular equation. Now, when it comes to the complete ionic equation, I break up anything that has the AQ symbol in front of it that's an ionic compound. So barium nitrate, potassium sulfate, and potassium nitrate are all going to break up, but barium sulfate will not because it has the solid symbol. So I write all of these ions out. Remember, there's 2 nitrate ions here, so I write 2 in the nitrate ion. And I list it all out like this, and then I identify the spectator ions. Well, nitrate and potassium show up in the same form on both sides, so I cancel those out to get me to the net ionic equation, which is simply barium plus the sulfate ion gives me barium sulfate. And that is then my net ionic equation. Let's do one more example. So write the net ionic equation for the reaction that occurs when aqueous solutions of calcium chloride and sodium carbonate are mixed. Again, we have to know our nomenclature. So calcium chloride and sodium carbonate, we'll write both of those. The molecular equation, calcium chloride, it's aqueous. Chloride, that's a halogen. Calcium's not an exception, so this is aqueous. Carbonate, now those are normally insoluble, but sodium is an alkali metal cation, so this is soluble. And then I would write out my precipitation reaction as normal. Calcium carbonate is an insoluble combination, so that forms and leaves me with sodium chloride. The complete ionic equation is simply I go through and break up all of the aqueous cases that are ionic. And so calcium 2+, 2 chloride ions, 2 sodium ions from there, 1 carbonate ion. Goes to calcium carbonate does not break up because it is a solid, not aqueous. And then sodium and chloride break up into 2 sodiums and 2 chlorides. I identify my spectator ions, which happen to be chloride and sodium. Chloride shows up in the same form on both sides. Sodium shows up in the same form on both sides. And then I cancel those out and write my net ionic equation as simply being the calcium ion plus the carbonate ion forms calcium carbonate. And this is how you write complete ionic equations and net ionic equations. I highly recommend reviewing this video in detail and practicing with the homework for writing complete and net ionic equations.